Assalamu alaikum students. I am Abida and I am going to teach you Analytical Chemistry 2 Chem 508. So the topic of today's discussion is absorption of radiations by matter and electronic transitions. In the previous lecture we have discussed in detail the interaction of electromagnetic radiation by matter and the properties of electromagnetic radiation and their relationship. So today we will discuss in detail that what happens when radiations are absorbed by matter and what type of electronic transitions can take place. So how does matter absorb radiation and why we see objects as colored? A qualitative picture of the absorption of radiation can be obtained by considering the absorption of light in the visible region. So qualitatively, the objects we see as colored because they transmit or reflect only a portion of the spectrum of white light when illuminated by white light. So what happens actually when white light falls on an object? The object will absorb certain wavelengths of the light and the remaining light will be transmitted. So when polychromatic light, which we also call as white light, which contain the whole spectrum of wavelengths in the visible region, passes through an object, the object absorbs certain of the wavelengths, leaving the unabsorbed wavelength to be transmitted. So as I have already said that when white light it will fall on an object, then object will absorb only a portion of that visible light, and the remaining light it will be either unabsorbed or we may call it as transmitted light. This transmitted light, this is called the complementary of the absorbed color. So what will happen that a portion of that light will be absorbed and some portion will be transmitted. So this transmitted light, this is called as complementary of the absorbed color. In a similar manner, opaque object will absorb certain wavelength, leaving the residual light to be reflected. But in case of opaque object, most of the light will be absorbed and only a limited portion will be transmitted. And in case of black objects, all the light will be absorbed, and thus we see the color of this thing as black because no light will be emitted. So we will see only black as a color. So for example, if we have a solution of potassium permanganate, this will absorb light in the green region of spectrum and it will have absorption maxima of 525 nanometer and solution will appear purple. So in case of potassium permanganate, what will happen that the absorbed light will be in the region of 525 nanometer, which is of green color, and the reflected color or the transmitted color which we see, this will be purple. So basically there are three types of electronic transitions. Number one is rotational, which is of lowest energy level, and then vibrational, and then electronic transition. So how these three basic type of transitions can occur? There are three basic processes by which a molecule can absorb radiation. In all cases, the molecule is raised to a higher internal energy level, the increase in energy being equal to the energy of absorbed photon h nu. So in a molecule actually we have a different energy level, electronic energy level, vibrational energy level, and rotational energy level. So in an electronic energy level we will have we will see shortly, we will have vibrational energy level, and in vibrational energy level we will have rotational energy level. and energies of all these electronic transitions, that is from one electronic transition to higher electronic transition, or within one electronic transition, from one vibrational energy level to another vibrational energy level, or within the same vibrational energy level, rotational energy level to another rotational energy level. Energies of all these transitions, this is quantized, that is definite amount of energy having value h nu is absorbed. So we will have therefore for each transition we will have definite line which will represent these absorption transitions. The three types of internal energies are quantized. By quantized we mean, again, I wanted it to explain that from one electronic transition to the other electronic transition, the energy is quantized. That is, the molecule will absorb only that amount of energy which is equal to the distance of energy between two electronic transitions. That, for example, if we have ground state electronic transition and we want to move electron to higher energy level, then the molecule will absorb only the difference of energy level between E naught and E1. We will see ahead. That is, so there exist discrete energy levels. First, the molecule rotates about various axes, the energy of rotation being at definite energy level. So the molecule may absorb radiations and can be raised to a higher rotational energy level in a rotational transition. So in rotational transition, molecule will go from one rotational energy level to the other rotational energy level. And secondly, the atoms or groups of atoms within a molecule vibrate relative to each other, and the energy of this vibration occurs at definite quantized level. The molecule may then absorb a discrete amount of energy and be raised to a higher vibrational energy level in a vibrational transition. So thirdly, what will happen? The outer shell electron of a molecule, valence electron, may be raised to a higher electronic energy corresponding to an electronic transition. These transition will be referred to as electronic transition. When an electron in the valency shell, in case of electronic transition, it can excite from E naught, that is lower energy electronic state, to E1, that is excited energy state, then electronic transitions will take place, and obviously the energy required for these transition is higher than required for vibrational or rotational energy level. And this occur in UV visible region of the electromagnetic spectrum. So what will happen, that at still higher energies, that is visible and ultraviolet wavelength, different levels of electronic transitions take place, and rotational and vibrational transitions, these are superimposed on these. The result in an even large number of possible transitions. Although all the transitions occur in quantized steps corresponding to discrete wavelengths, these individual wavelengths are too numerous and too close to resolve into individual lines or vibrational peaks, and the net result is a spectrum of broad bands of absorbed wavelengths. What it means actually, in case of if we have energy sufficient for electronic transitions, then accompanying electronic transitions we will also have vibrational, rotational and vibrational transitions. And all these transitions, although they are quantized, that they will only occur when the difference of when the radiation having the difference of energy required for rotational, vibrational or electronic transition, then we will have these transitions, but anyways they will occur. So if we have the energy we have necessary energy required for electronic transition, then rotational and vibrational transitions, they will also occur. So the result, what will happen actually, that all these transitions, they will superimposed, that we will not be able to resolve these transitions, and there will be too numerous and too close transitions that we are unable to resolve these into individual lines or vibrational peaks, and the net result is a spectrum of broad bands of absorbed wavelength. So we will have actually absorbed we will have broad bands, and typical visible and ultraviolet spectra we will discuss in the next lecture. Due to lack of fine structure, UV visible spectra are not particularly useful for structural determination. However, they can be used for combination by comparison with the spectra of putative compound. So in the next lecture, I will show you different types of spectra in the infrared region, and then also in the UV visible spectra, and we will see that in the IR region, the vibrational spectra, which are relative to the identification of the functional groups in the compound, while in case of UV visible spectra we will see broad lines as written here, and these are not of so much analytical use, but in the literature various spectra are present. A large number of spectra actually are present, so we can compare and match the spectra of the compound we want to identify. Then we can get some information which can be useful for structural determination. Thank you.